Now it's to record. So welcome everyone to this second verifiability talk. It's my honor to introduce Jim Woodcock. Jim is a professor of software engineering at York University, and he has held various positions in the past at Oxford and also at University of Kent. I have studied his textbook long ago when I was a graduate student, and also I was his student at Mark Oberdorf Summer School when he taught us circus. But today he will be talking about one of the foundations of our node, which is a unifying semantic framework for verifiability. And I guess there are lots of interesting challenges when considering autonomous systems and establishing trust in them. So without further ado, I give the word to Jim Woodcock. Jim, the floor is yours.
Mohammed, thank you very much indeed for the introduction, and hello everybody. I can't see any of you. As Mohammed says, I'm going to talk about a unifying semantic framework for verifiability. And I know that our last seminar, the first seminar, Louise talked about some particular verification tools and techniques, and I'll be talking about a framework for those sorts of things to bring them together. So my talk comes in these short sections. I plan to spend about 40 minutes talking, and then we can have a discussion afterwards if you like. So I'll start off by talking about the background to this work. And in the proposal, we put forward a vision of a verified autonomy store. And I'll give some background as to why that's an interesting thing and how it's a long way in the future. And then I'll talk about our approach to this work, which is a unifying framework, unifying semantic framework. And I'll talk about cases, which is to do with verifiability. And I'll talk about our research plan for work package 2, which is what my talk is related to. And I'll draw a few conclusions at the end of it. So I'll start off by giving some background. And what I'm going to do is I'm going to hope to be able to show a little movie. There we are. Start that movie up.
Are you the owner of a brand new robot? Congratulations. Now that you've learned its functions and played with it for a few hours, though, you're probably starting to wonder, can it do anything else? What if you had a way to teach about new things? Things you and he never dreamt were possible? Then you found the right place at the Robot App Store. Just like downloading apps for your smartphone or your tablet, you can now download apps for your robots. Imagine turning a pile of Lego, a surveillance vacuum, a demolition machine, and a now robot into just about anything you can imagine. If you've got a robot, we've got apps for it. Come in and browse around. Apps are searchable by robot, sensor, programming language, or by category. You can also create your own apps and submit them as part of the marketplace. Don't know how to make an app? Confused about how to download applications? No problem. Check out our knowledge base for how-to questions, or examine our Robopedia to learn the basic terms of robotics and programming. And of course, we're always here for you, so don't be afraid to ask. You can always visit us at www.robotappstore.com, and welcome to the Robot App Store.
Okay, so that was just a little taster of a real robot app store. And I'm going to be talking about our vision for an autonomy store, a verified autonomy store. So in that movie, you saw the Robot App Store. They describe themselves as the first app store for applications for robots. With Robot App Store in the cloud, your robots are always up to date with the coolest apps. And who wouldn't want to have a cool app? This is a digital app distribution platform for robots. And it's a kind of existence proof of a model for using and exploiting robots, which I think is quite interesting. So users browse and download apps published through robotappstore.com. And the business model, roughly speaking, is that the developer offers some apps for free or at a cost. If they go for free, then there may be some in-app purchases or some advertising. The apps can be downloaded to a robot, a computer, or a smartphone, and 70% of the sale price goes to the app developer. It's available to developers and robot owners around the world. And you saw that there was also this Robopedia, a centralized encyclopedia for robotics topics with a comprehensive knowledge base and development lessons for popular robotic platforms. Now, the reason why I think this is interesting is from a business point of view. If you look at the App Store for mobile phone apps, just the Apple one, of course, there's the Android one as well. In spite of the fact there are far more Android phones than there are Apple phones, the turnover for the Android App Store is about half of what I'm about to show you. So the estimated commerce facilitated by the Apple App Store ecosystem worldwide last year is just over $500 billion US. It's an enormous amount of money. But that's misleading because a lot of that is about physical goods and services being sold through the App Store. If you restrict it to digital goods and services and in-app advertising, you get more than $100 billion US. And if you want to know whether you've got a disruptive technology, $1 billion company is a sign that you have. And here, the App Store is $100 billion, right? So it's 100 times that kind of benchmark. So that's an interesting thing. Could we replicate that success with robots? So why should we have a robotics app store? And I'm thinking about something much more interesting than the one that I showed you. So why have a robotics app store? There are several reasons. The first is about new economic models for robotics, and that's about monetization. If you compare robotics with other sorts of electronic consumer electronics and products, you'll see that there's a very interesting economic model which is to do with hardware and software. Make the platform low cost, but it's no good without software control. So you continually have the user downloading apps to do interesting things with the robot. And so the idea is to have general purpose platforms and even personalized functionality. And I think that's a really interesting thing. Also here, you want to, if you're a robotics company, you want to future-proof your robots. So the market might have all sorts of interesting developments and you should be able to react to it. So having a robot app store is a good idea there. And then coming back to the iPhone app store, there are economic models to do with not just purchasing the app, but in-app purchases. And then very interestingly, in-app advertising. How about that? In-app advertising on your robot. Now they've got to find the right way, the most acceptable way of doing it, but I don't doubt that they will. I'm sure there are new economic models around all these ideas. The second reason for having a robot app store is to do with efficient distribution of updates. So I remember when Java was first released, I went to a big conference to launch the language in Berlin, and they were talking about DHL, who were using early versions of the language and early versions of apps to track parcels. And they wanted to be able to distribute software around the world and always be up to date with new versions. And it was really significant that they could do that with Java. And of course, that efficient distribution hasn't gone away. It's a really important thing. New versions of software, but also patches to solve problems with safety and security and functionality. Another reason, well, if you've got a robot in an inaccessible location, it may be keep it up to date is going by having app downloads. And there's no direct way you could keep it up to date. And then finally, here in York, we've got some people who are very interested in flexible firmware and flexible hardware. So if you want more functionality from your robots, you might even download the instructions to a 3D printer and print new add-ons, hardware add-ons for your robot. So these are all reasons why you might have a robot app store. Here's another economic model for cloud-based robotic services. And the example I've got here is in adversarial objects. In the picture on the left, are a number of objects that have been designed to be hard for a robot gripper to pick up. And this photograph comes from Goldberg in the Auto Lab at UC Berkeley. And he calls these physical adversarial objects by analogy with adversarial attacks on learning components in machine learning. These are tricky for grippers to pick up, and a small tweak, a slight variation in these shapes could spell disaster for the robot, especially if it's doing something interesting with the object. Now, Goldberg calls this a stupendously difficult problem to be able to pick up adversarial objects like this. So here's a bright idea: outsource the computation. So the robot sends a 3D image to the cloud, a supercomputer works out what to do with the object, and the server returns some grasping instructions to the robot. And now every robot, even a really dumb one, becomes a supercomputer with fantastic abilities to handle these sorts of objects. So cloud-based robotic services looks like a very interesting economic model. But of course, you need the right app and you need a good internet connection. So app stores also have risks associated with them. Downloading software is clearly a risky business. You need to guard against malware, against malicious software. And that's where our verifiability research comes in. You've always got to be worried about someone monetizing you, exploiting you, endangering you. So malware lets someone take control of your robot. And there are examples all over the place now of hackers hacking autonomous systems of one sort or another. And hackers can have access to your contacts, to your passwords, to your financial accounts, all the usual security and safety issues. But there's more. Robots sense and change the real world. So hackers can not just have access to your goodies, they can also change your environment around you, and perhaps in really unpleasant ways, and you won't like it. So just say no to downloading software to your robot. But I don't think we will we? I think the idea of this app store is really very compelling, and it's the way that a lot of robot companies are going. So I looked up some research issues in verifiable robotics, and I found this report, the Multi-Annual Roadmap for Robotics 2020. It's from Horizon 2020. And they put down a whole load of issues to do with verifiable robotics. So these are in the form of questions. What are the models for safety verification of robotics? Here, ISO 13482 is a standard for medical guidelines for personal care robots, the sort of robot who's going to put your granny to bed, right? So what are the safety verification techniques for showing that you're compliant with this kind of standard? Not this one in particular, there are many interesting industrial standards, and this is just an example. So what are the verification techniques that accompany the standards? What are the automatic methods to verify the safety of modular robots? And the App Store is partly about modularity, importantly about modularity. What are the verification techniques for components and systems and applications? What are the methods and tools for implementing multiple instances of a system or for adapting to specification changes? It observes that there are really good tools for some of the problems that we face, like requirements engineering and graphical design and design verification and component compatibility verification, which is the feature interaction problem, and model-based verification and code generation and so on. But how do you get a unified tool chain that brings all those together? And I've got a lot to say about that in a few slides' time. What are the methods for reasoning about quality of service? And then finally, what are the model-based verification methods for development? So this is about automatic translation from system design to deployed runtime systems. And the roadmap highlights what the barriers are here. Lack of formal verification methods and tools, lack of safety validation and testing methods and tools, and lack of community awareness for industrial safety standards. And the report puts forward an action plan for the things that we need to cover in research and bring about as practical techniques. So formal specification and synthesis of control systems, formal proof of behavioral properties of cognitive robotic systems, and formal proof of safety properties for cognitive robotic systems, formal development methods for control systems for robots, and rich modeling, not just of robots, but of their hardware and their control systems and their environments and their tasks, all together in some coordinated way. And system verification, including the really important technique of runtime performance monitoring and failure diagnosis. So that's the barriers and the actions they believe the community ought to be taking. What I'll do now is I'll move on from that background and I'll start talking about the vision that we had when we wrote the research proposal of a verified autonomy store. So here's the vision. Within 10 years, we'll have a verified autonomy store. What we're going to do, of course, is not produce such a thing. We're going to produce the foundational research such that it looks feasible within 10 years to have such a verified autonomy store. The vision is that this store will be a repository for verified autonomous systems and autonomy components for building systems. And the idea is when you deposit something in the repository, when you submit it, it'll be subjected to rigorous and extensive verification and certification against standards. And as you evolve, because all computer-based systems evolve, as you evolve, the autonomous system or the autonomy components will be subjected to further verification and certification. And there are big challenges there to be able to do that. So we'll be talking about components and system packages for hardware and for software and for design models and all sorts of artifacts to do with platforms and environments and system level and component level properties and verification evidence and certification evidence. And what really interests me a lot is how you have updates of models and updates of these components and systems. And so the autonomy store will have automated facilities for verifying model updates to take account of new algorithms, new platforms, environments, and components, to take account of adaptive and evolving behaviors and changing and extending functionality, and taking into account new verification evidence and new test results from deploying the autonomous system in the real world in a live environment. And all this requires dynamic assurance. Dynamic assurance is not something that's accepted by any regulatory authority at the moment. So there's really important research that needs to be done here. And we need to be able to convince regulators that this is something worth doing. And you see work, for example, at NASA in this area. And it's regarded as being very, very important, particularly for space vehicles. So here's our project on verifiability, at least my take on what we're doing. Our aim is to verify complex autonomous systems. Our goal is a unifying framework for rigorous verification techniques. And our objective is to provide strong guarantees for trustworthy autonomous systems. Now, components will be subject to variability and evolution, and also interoperability. You might need to change a component because it interacts with another one that's changed. So you get this knock-on effect. There'll be system-level properties for composing components. And the components and the systems will have properties that are reactive and real-time, adaptive, and there'll be uncertainty both in platforms, hardware, and in the environment. And we'll want guarantees for functionality, but we'll also want guarantees for safety and security, and in particular, safety and security cases and ways of maintaining and improving those cases. So the life cycle vision I've got is that the autonomy components and systems will start off being assured. They'll be developed and deployed, they'll evolve, and there'll be a continuous process of dynamic assurance. And this is the way to generate and maintain trust. And this will be at every abstraction level, from planning and AI all the way down to hardware and physical control. So we're talking about an autonomy store with trustworthy systems and cheap and trustworthy components. cheap because we've been able to automate a lot of the verification and shoulder the risk that otherwise people would have to worry about. And so our project is focusing on foundational research to enable verification activities to bring all this about. This requires integration of verification techniques across hardware platforms, across different kinds of software control, across uncertain environments, and including user interactions. And it mustn't be specific to any particular platform, any particular standard, or any particular notation. My next slide is about the challenges you get from cyber-physical systems, especially autonomous cyber-physical systems. The development and deployment of such systems, autonomous cyber-physical systems, requires a much deeper integration of different design disciplines than traditional systems do. And of course, by definition, they combine the physical and the computational domains. And so the main challenge in CPS design is in heterogeneity of the components, of the design techniques, of the disciplines that are contributing. So in components and systems, you see multiple aspects that are physical, that are logical, that are functional, and that are non-functional. And you see physical properties to do with structure, to do with mechanical dynamics, thermal properties, propulsion units, hydraulic components, electrical components, acoustical components, and vibration properties, all these sorts of things. And in the computational and networking domain, you have to worry about system control, you have to worry about sensors, maybe managing health, maybe managing the mission, maybe communication between the components. So the challenges here that arise from autonomous cyber-physical systems, the challenges are in modeling and analyzing cross-domain interactions and composing heterogeneous abstraction layers. The first of those two is, if you like, the horizontal direction, and the second, if you like, is the vertical direction. And the proposed approach we have in our project is a unifying framework. So let me talk about that, a unifying framework. Here are the research challenges for this part of the project. There are other really important parts of the project, and I guess in future weeks we're going to have research seminars on those. So this is about the part of the project that I'm presenting. So here are some research questions. How do we link together diverse computational and physical paradigms? Okay. How do we link together semantics at different levels of abstraction? So we need the first of those to link together the cyber and the physical and the environment, right? We need the second for development and abstraction. So going down to turn our requirements into deployed models and deployed robots, but also going up to find abstractions that we can reason about. Now, suppose we have a unifying framework that has those two dimensions. How do we mechanize it? How do we use it to build sound tool chains? How do we make the framework both open and extensible? And how do we use the framework to link techniques from the other research nodes in the Trustworthy Autonomous Systems program? So those are the research challenges. Really interesting questions. So here's the framework that I have in mind, and it's got three aspects to it. In the left-hand column, we've got models. Down the middle, we've got verification techniques and tools. And down the right-hand side, we've got a unification technique. So if you look at the models column, I'm thinking about models for software, for concurrency, for probabilistic behavior, for hardware, for the environment, and also heterogeneous combinations of these. So for software, you might be using ASM or B or VDM or Z. They're popular sorts of languages and tools in this area. For concurrency, you might be using Petronets or CSP or CCS. Probabilistic behavior, most likely you'll be using some kind of Markov decision processes. In hardware, you might have a signal-based language like Simulink, or an object-oriented multi-modeling method like Modelica. And in heterogeneous modeling, you have languages like Robochart that bring lots of these things together. For verification, you want to have techniques and tools for model checking to prove things about these models. for theorem proving, for simulation, and for testing and validation. So for model checking, it might be model checkers like Prism and Storm for Markov decision processes, and FDR for concurrency. For theorem proving, it could be Isabelle or Coq or Lean or PBS. And for simulation, we might use some industry standard simulation like Gazebo, Weebots, and VREP, or some more research-oriented simulators like the Into CPS toolset or RoboSim. And for testing and validation, there's lots of different tools and techniques. So the third column about unification is about taking the semantics of those models, taking the semantics of those verification tools, and somehow integrating them. So integrating their formal semantics. Now, I very much doubt a single semantics would be appropriate for all this variety of different techniques. And it would be difficult to make it open and extensible. Too many competing issues. So what I have in mind instead is a way of bringing all the tools and semantics together and then using them in some coordinated way. So they still retain their individuality, because that's very useful, but they can be used in a coordinated way, like the Swiss Army penknife that has many tools that can be used together. The saw, and then you can smooth things off with the file, cut off bits with the knife and so on. Use one tool after another and have a combined effect. Now, there are two principal techniques for integrating formal semantics. One is institutions, and the other is unifying theories of programming. And I'll talk about them next. So I'll compare these two things in order to explain what they are. Institutions against UTP, unifying theories of programming. So institutions was this theory, this meta theory, was created by Joseph Goguen and Rod Burstall in the late 1970s. I remember going to a talk in 1984 where they presented their work in a conference at the University of Surrey, and it was very, very exciting. They said they wanted to deal with the population explosion in logical systems in computer science. So they wanted to capture the essence of a logical system as a so-called institution. And this is a way of formalizing a specification language. And it could be a discrete language, it could be a continuous language. All sorts of different paradigms can be formalized in institutions. And so if you take the specification language and formalize it like this, you can look at maybe specification structuring and parameterization, or maybe the vertical direction, refinement, development, implementation, and deployment. And you can also look at the combination of proof techniques and proof tools. And you can do this independently of the underlying logical system. So the basic idea is to have theories that are connected together. And these connections are category theoretic morphisms that relate the logical systems and translate between them. And the applications here are in the reuse of logical structure. So you've got many different logics, and you can factor out of them some commonality and then put that somewhere else and inject it into these institutions as you wish. Another application is in heterogeneous specification. And the final application here is in logic combination. You want to prove something about your heterogeneous system, and you've got different logics to prove things about the different parts. How do you combine those and understand something about the combination? So next I'll talk about UTP, Unifying Theories of Programming. This is the paradigm where semantics is given to programming language and specification languages, hardware description languages, all sorts of things. And the descriptions, the programs, as we like to call them, the programs are predicates, so they're truth values. And this is built out of the alphabetized relational calculus. And whereas institutions has theory morphisms, UTP has something similar, Galois connections that link and translate between theories. And this gives you useful approximations. So here's an example. Suppose you have a theory of synchronous computation and a theory of asynchronous computation, and you want to be able to prove some results between these two theories. So you might have a Galois connection that maps you from the asynchronous world into the synchronous world. Well, how would you do that? Well, the synchronous world has a kind of barrier synchronization that comes down on every clock tick, right? And on that clock tick, you exchange information between different parallel processes. So you could turn an asynchronous parallel system into a synchronous one by scheduling, finding a schedule for all its operations, all its communications. Now, that wouldn't be an exact representation of the asynchronous world. It will be an approximation. But that's not a vague thing. It's a very precise thing. I understand exactly what the approximation is and what I'm losing and what I can rely on when I do that. And another thing for free is if you define this in one direction, do the easiest one you can, then you get the other direction for free via a construction that's part of the theory of Galois connections. So institutions unify logic, whereas UTP unifies semantics. That's the distinction between them. And for UTP, logics come afterwards, after the semantics. So UTP does some very interesting things. It unifies different semantic presentations, for example. So you know about denotational semantics and algebraic semantics and axiomatic semantics and operational semantics. 4 different ways of presenting the semantics, perhaps for one language. And what UTP says is, well, those presentations are different. They give you different information, but they are giving you the semantics of the same language, and we can map between them. So, for example, in process algebra, there are 2 very famous process algebras, CCS and CSP. CCS is given semantics as an operational semantics, and CSP as a denotational semantics. And UTP has been used to give an account of the connection between those, and some very nice observations about the expressive power of each language. Another example is in Hoare logic, you have Hoare triples that talk about a precondition, a program, and a postcondition. That's called a Hoare triple. And in Milner's operational semantics, you also have triples where you have a process before, you have a transition under an event, and you have a process afterwards. So again, a triple. And a rather surprising result from UTP is that these 2 triples that come from very different paradigms are really very much the same thing. And then finally, you can do a semantic round trip. You can start off with denotational semantics and derive an operational semantics. And the proof of correctness of the operational semantics will depend on the algebraic laws in your algebraic semantics. And then you can reconstruct the denotational semantics from the operational one. And that's the round trip that I'm talking about. And once you've done that, you know something very, very profound and deep about the consistency of the 3 semantics. I'm going to interfere with somebody's microphone.
Sorry, Jim, if you wait for a second, there is a bit of a background noise. Let me find out where that comes from. And yes, now it's fine, I think, right? Oh, no.
Oh, thank you.
Sorry, one more second. I think this is fine. Yeah, sorry.
Okay, so the take-home message from that little bit of theoretical consideration is that UTP can link together different sorts of verification tools, like model checkers that rely on operational semantics and theorem proving that relies on algebraic semantics with the soundness in denotational semantics. Second thing to note is that UTP scales up to industrial strength language semantics because of this way of composing individual semantic paradigms. And finally, I think there's considerable intellectual depth in relating the theory of institutions and UTP, but that's for another project. It's not part of the current project. So back to the autonomy store. There'll be a tool chain. I mentioned the tools that would be used to verify components and systems when they're deposited and as they evolve. So my slogan for the autonomy store tool chain is that we link tools through unifying theories. You see, individual tools have different semantic models. A simulator implements an operational semantics, a program verifier implements an axiomatic Hoare logic. But we can link these 2 together if we understand the semantics and what the connections are. If we don't, then we have a danger, and it's the formalization gap. Right? We've got a different semantics in this tool from this one. They might even be talking about the same language and use a different semantics. And that leads to an incoherent analysis and an ineffective verification. And what UTP is about a mathematical framework for formalizing and unifying these semantic models so that we have a layered approach to semantics supporting the different tools. So we link tools through unifying theories. And this means we could have a tool chain, a horizontal tool chain. You put a model in at one end, and out comes some deployed artifact at the other end, the models that you're going to use for your deployment for the robot. And in between, the output of one tool becomes the input to the next tool, and so on. Now, if you have an understanding of what it means for this tool chain to be correct, you can have end-to-end verified heterogeneous tool chains. And that's the prospect that UTP is offering. So I just wanted to say something about the existing and developing UTP theories. There's a theory of assumed guarantee reasoning. Now that's the theory of pre and post conditions and assertional reasoning. It's specific to sequential software usually, but the way that UTP theories get combined is that we can use that style of assertional reasoning in every other paradigm, including hybrid continuous discrete systems, for example, or hybrid synchronous asynchronous systems. We can use that same kind of verification and therefore the tools that go with it. So that's one theory. The second theory I wanted to mention was a theory of concurrency in communication. Parallel processes and how they exchange information. There's a developing theory of probabilistic modeling, and then some preliminary work on multi-domain modeling. This is the semantics of Modelica for mechanical descriptions and electrical and electronic and hydraulic and thermal and control and process-oriented. That's all I want to say really directly about UTP. Let me talk about how we mechanize UTP, because this mustn't just be a pencil and paper mathematical activity. We need to have tools for being able to manipulate and exchange theories. So Isabelle UTP is a tool for the mechanical support for formalizing UTP theories. And it allows us to have this unbroken chain from requirements through to deployment models, and to use Isabelle UTP as an arena for carrying out all the semantic work and the verification work. There's two ways you can use a tool like this. One is in theory engineering, and the other is in model verification. So building and exploring the properties of theories, but also using those theories to produce models and to verify them. And Isabelle UTP is for both these purposes. It's a novel mechanization of UTP in the Isabelle Hull theorem prover. And it's a deep model of the alphabetized predicate calculus, the alphabetized relational calculus I mentioned before, integrated with the Isabelle type system, and all supported by high-level proof tactics, which are very powerful. So here's what I think you can do in Isabelle UTP as a unifying semantic framework for verifiability. You can create theories, you can do semi-automated proof of properties, you can do theory combination, and you can do model transformations, refinement in the vertical direction. Here's a picture of what I'm talking about. Imagine at the bottom of this picture, you've got Isabelle Hull, the theorem prover that has been around for 25 or 30 years. So it is really very well trusted as a piece of software for doing sound proofs of theories. Now, built on top of that is the alphabetized relational calculus. And then built on top of that are different theories like assertional reasoning, concurrency, hybrid behaviors, and so on. And each of those theories is expressed in alphabetized predicates, all in Isabelle UTP. And so we can combine those theories to make a denotational semantics. And from that, we can build operational semantics and axiomatic semantics. Why do we do this? Because there are particular tools like compilers and interpreters. Compilers, like code generators, and interpreters like simulators and animators and so on. They work on the operational semantics. Now, how do we know that we're generating the right code? How do we know we can trust it? Well, because that code generator is a kind of compiler that's correct, that's sound because of the operational semantics. And the operational semantics is sound because of the denotational semantics. And the denotational semantics is sound because of the theories, and they are sound because of the alphabetized relational predicates. And that's sound because of what's underneath in Isabelle Hull. And similarly, on the other axis here, if you go up through the axiomatic semantics, there are tools that rely on the axiomatic semantics, like Hoare logics and weakest precondition semantics. And they're things like refinement calculators for doing that vertical trip, translating designs into lower level designs, architectures into components, and all these through into deployment models and so on. And of course, there are verifiers. And these tools are sound because of the axiomatic semantics, which depends on the denotational semantics, which depends on the theories, which depends on the alphabetized relational calculus, which depends on Isabelle UTP. So there's the UTP Semantic Stack. And you see our approach to a framework for verifiability. This is the framework. So here's an example. Autonomous systems, we would like to be able to describe them in useful and interesting ways. So for example, hybrid dynamical systems for describing the hardware, the way that it reacts in a physical environment, and how it can be subjected to control and feedback and so on. So here's a group of theories. The design theory, that's the assumed guarantee reasoning. The reactive theory, that's the theory of concurrency and communication. Now, if you inject the design theory into the reactive theory, you get reactive designs. So it's a combination of those two theories. So now you've got assertional reasoning in a discrete theory of concurrency and communication. Next, you take the hybrid relational calculus, which is just the ordinary relational calculus extended with continuous variables. Now, an abstraction of the reactive theory provides a generic trace model for reactive designs. And if you take that generic trace model, you can make a hybrid reactive theory by taking the trace not as a trace of discrete events, but a trace of piecewise continuous functions. And now you've got a theory of hybrid reactive systems, and you can use it to give a semantics to hybrid CSP, for example, where you have continuous evolution of state variables within discrete events and concurrency. And what Simon has been able to do is to integrate Platz's differential induction technique into Isabelle UTP to give a powerful way of reasoning about designs in this hybrid language. And future work is going to take one of the languages I mentioned before, Modelica, and give a good way of specification and verification based on that language. And that will be a dynamical systems modeling language. Now, let me talk briefly about assurance cases. Here's, again, Simon's picture for a vision for using the framework for verifiability and assurance at the same time. So imagine that you're implementing an autonomous system, and you start off in the left-hand column with terminology. So this is a domain engineering exercise to find the vocabulary of your autonomous system, in which you can articulate some requirements, and then you build models of the autonomous robot using something like RoboChart. And so you might have a data model and an architectural model and a behavioral model. So the idea is to use Isabelle to integrate all these semantics in Isabelle UTP, and then to provide assurance cases and generate from the assurance case a certification document. So here's the idea. On the left of this picture is a diagrammatic language called the goal structured notation, which is now an international standard, the structured assurance case meta model, SACM. So on the left, you have a picture that's arguing about safety. The system is acceptably safe if all identified hazards have been mitigated. To demonstrate that, we have an argument over all the identified hazards, and each of those is shown to be sufficiently mitigated. And some of that argument might be a formal verification, and some might be an informal argument, inductively obtained and using informal information. On the right of this picture is in Isabelle SACM, this version of Isabelle that's got the goal structured notation embedded within it. There's a formal argument for what's going on the left. But you say, no, that can't be right because hazard H2 doesn't have a formal verification. No, but what's going on the right is that the argumentation is formal. The formal parts of it, the ones that do have formal verification results, are also formal artifacts. But there's room in this for informal evidence as well. And that's what you need to do for some systems. That's part of verifiability. So Isabelle SACM then is an implementation of safety case arguments in Isabelle, which is supporting the automated construction of model-based assurance cases using integrated formal methods where we can. And we know that UTP is a suitable framework for that. So an assurance case shows how a system is safe to operate or secure in its operation. And there's a human comprehensible argument that the requirements are satisfied. And the evidence might have various provenances. Often that'll be formal, but this approach also allows for informal parts where you can't formalize it. And all this is required for the certification of critical systems. And automating the assurance case, automating the argumentation is essential for verifiability, for maintenance, and for evolution. And this is based on an ontology framework called Isabelle DOF, which encodes the SACM meta model. And the key idea for our project is to extend Simon's work on static safety cases in Isabelle and produce dynamic ones. And so that goes back to what I was talking about in discussing the autonomy store. So we can use Isabelle DOF, this ontology tool, to record a database of artifacts, of deviations from specifications in operation, and other interesting events. And this will be a novel use of the Isabelle theorem prover as an orchestration engine to generate and manage artifacts. And then my vision here is to use Isabelle SACM and Isabelle DOF and Isabelle UTP as dynamic assurance case managers, and for the models to do with an autonomous system. And that would then give you a way of organizing all the models and information you need for digital twins. So I'm almost there now. I'm going to talk about the research plan, which comes in 3 parts. Here's the first part. Our plan is to produce a UTP framework for the horizontal linking of verification techniques. And in particular, we'll define and link the following dual paradigms: discrete and continuous, synchronous and asynchronous, algorithmic and learning, adaptive and evolutionary, and 2 kinds of uncertainty, epistemic and aleatory, and link all these dual paradigms together. And this will underpin the semantic issues we find in trust and responsibility and resilience and security and functionality and governance and regulation. And the deliverable here will be a formalization of the paradigms for heterogeneous semantics and links between these framework elements. So that list of dual paradigms is our heterogeneous setting that's being given by our framework. The second part of our work plan is about the vertical direction, the refinement of heterogeneous languages. We plan to extend the framework to link different levels of abstraction. And this will give us abstraction levels for requirements and planning, architectures, control algorithms, hardware, and deployment. And the refinement theory will be sound. It'll be based on our semantics from the previous work item, but it will be inspired by practical examples taken from our case studies and other examples. And the delivery here, the deliverable, will be a refinement theory for heterogeneous semantics. And finally, the third part of the work plan is in linking tools. Now, I gave you this slogan, linking tools by unifying semantics. This will be a practical and sound method for building tool chains. There'll be a semanticist toolbox for mechanizing frameworks in Isabelle UTP, and support for linking real tools used in real case studies and in other nodes. And the deliverables will be a method for linking tools, some example tool chains that are linked, and the Isabelle UTP theories, the mechanized theories for the unifying framework. And that is almost all I have to say. I just want to draw a few conclusions, and then I'll stop. What I've told you about is a verification framework for interdisciplinary autonomous systems based on unifying theories of programming and exploiting Isabelle in 3 different ways. It'll relate verifiability concepts and their notations and their techniques, and it'll integrate verification across different disciplinary domains. It'll provide dynamic assurance techniques, and it'll give you a way of managing an autonomous system towards the creation of a digital twin. And finally, it'll give you an ecosystem of verification techniques for some of the things I mentioned: functionality, and resilience, and security, and ethics, just to go back to the last talk. And so that's the final thing to say, is that I've been talking about a verified autonomy store. Remember, that's a future ideal, and all the work I'm proposing that we undertake is to get us towards being able to produce such a thing that might well have significant commercial ramifications. So that's it. Thank you.
Thank you very much, Jim, for this very interesting talk. So we have a few minutes for questions. Are there any questions from the audience? Yes, I see hands up. Please feel welcome to unmute yourself. Raiko, please go ahead.
Yes, thank you. Can you hear me?
I can.
Yes, we can hear you. Yes.
Okay. So yeah, Raiko Heckel here. So I'm interested in the relation between institutions and unifying theories, even if you said you didn't want to talk about it. So just to understand the vision there. So do you thinking of these as sort of horizontally structured, in the sense that you have, I mean institutions are basically for logics, even
Yes.
if they can be used for some more operational formalisms as well. But clearly the unifying theories are more suitable for these operational semantics types formalisms than institutions. So do you think of using them for their various sort of specializations, or do you thinking of some kind of vertical combination where the institutions become a layer in your semantic stack somewhere?
I think it's a very interesting question. Thank you for posing it. I imagine that when we're linking together interesting paradigms in UTP, which might be vertical or horizontal, that we might take inspiration from institutions that has a different treatment for combining logics. And so when we're thinking about our semantics and what logics are supported by that semantics, it may well be that institutions give us a way of doing that. And I think there's a very interesting piece of work, which is, what would a unifying theory of programming look like if it was based on institutions right from the beginning? And that would give us an alternative way of approaching some of these problems. And from a scientific point of view, that's really interesting. I think from an engineering point of view, it makes good sense actually to use at the moment UTP and not institutions. There's a lot more experience in engineering theories in UTP that are useful in the kind of practical context that we're interested in than I think there is in institutions. There's a lot of really good theoretical work in institutions, and perhaps in the future we can take advantage of some of that. Okay,
so it's more a question of convergence to some extent rather than sort of plugging them together. Okay.
Yeah.
All right.
Thank you very much.
Thank you very
so
much.
I didn't record actually who was first, but I think Ian Gray was first, and then Mark Post. Ian, please go ahead.
There we go. Activate my thing. I know you said that the App Store type idea was kind of like a future-looking thing, but nonetheless, I'm going to jump right in on that and focus on something that got me thinking as I was listening. Sort of a key idea of the App Store from almost, if you will, from a user's perspective, is the idea that these apps are composable. So they have with them a security model and an execution semantics and stuff that inherently means that you can download a few and put them all together. Now, because this isn't entirely my area, what I wasn't necessarily clear on is how you would capture not just simply the verifiability of the actual things that you would be downloading from this kind of store, but how you would then be able to reason about their composition on a given platform, for example. Could you just sort of like point me in the right direction for those bits, please?
Thanks again for the question, Ian. It's a nice question. So here's an example. As you know, if you use Instagram and Facebook and your email and your website and blogs and so on, they all have different privacy policies. So a really important thing when you're composing apps might be to understand how to compose privacy policies. And I think that we're quite good at describing individual things. And what UTP is very good at is describing compositions of models. So if we can isolate each of those privacy models, we can understand how to compose them and then reason about that. So it would be a joint model. So what would it mean? Can you translate some privacy issues from this app to that app? And if you take all these 6 apps, is there a way of getting more information, synergy from the apps than you do from any individual one? And of course, the answers to both of those are yes. So this would be about taking the modeling techniques for privacy from the security research node and being able to find ways of composing those sorts of policies. And I think that's true for all the kinds of apps I would talk about. Privacy is just a particular example, but I think it's that compositionality that's what the UTP treatment of the App Store is giving you and is absent in a lot of other work.
Okay, thank you. Mark Post, please.
Hello. Very nice talk, Jim. Thanks very much. And I'm particularly interested in the semantics, which is a word that's been used quite a lot. You talk about the semantic connections, linkages between different domains, different languages, to form this unifying framework. And it seems to me that's a very important part of the automation aspect, as well as the ability you could do a lot with the information that you gather and the way that it's processed. Do you have any ideas how this semantic framework would look, or what sort of, I suppose, language or format you might use for these semantics? Is it something that we could do, for example, with RDF, Resource Description Framework, or do we need a new way of describing knowledge that we can use between these kind of systems?
I'm not familiar with RDF, I'm afraid. Somehow I feel I ought to be, but I'm not familiar with it. But the work so far has found ways of modeling different levels of abstraction and different computational and physical paradigms using this so-called alphabetized relational calculus. Now, I think you can write down domain-specific languages that would be more familiar and helpful to real practicing engineers. And one of the pictures I talked about, I started at the top with some domain engineering, understanding what the concepts are in a particular domain. And once you've got that vocabulary, you can then start to put them together. But that also applies to vertical development and horizontal linkages as well. You want to be able to take concepts from one area and translate them into another area, or from one level down to another one. So for example, if you go down a development, each of the layers might be characterized by some kind of healthiness condition that says what it means to have this computational paradigm or this physical kind of phenomenon. And these are healthiness conditions that constrain the behaviors. If it's in the real world, it makes sure they are real phenomena, right? They behave like things do in the real world. If it's in software, it may be some restriction in the language. You know, you can have this kind of concurrency, but not that kind of concurrency. And as you go downwards, you accumulate more of these healthiness conditions. Things become more restrictive. And so you can use the healthiness condition as a function on one layer to translate things from the upper layer down into this one. And that's where you get refinement calculi from. You can also use these sorts of things to take one theory and inject it into another. So I mentioned assertional reasoning with pre and post conditions. I also mentioned reactive processes that have concurrency and communication. And you can use the healthiness conditions for the reactive world to make all these little programs that exist over in this pre and post condition world, make them healthy enough to live in the concurrency world. So they behave in the way that you want. So for example, no shared variables and only sharing information by exchange of communication, if that's your thing, right? But those are the sorts of healthiness conditions that would arise. So it's about translating these, but I hope that it wouldn't be totally obscure if you start off with some kind of domain engineering and get the concepts for the application area right.
Okay,
Thank you.
so I think given the time, we should stop here. Although I'm sure there might be other questions that haven't been asked. I have several questions, but let's stop here. And of course, we will have 3.5 years to look at these concepts and interact more. Thank you very much again, Jim, for this very interesting talk. I think we all learned a lot, and we are very enthusiastic about building these foundations together. So thanks again. The next verifiability talk will be by Rob Hirons. It will be in 2 weeks' time, and I think tomorrow the announcement for that talk will go out. So we are very much looking forward to the next one.